Thanks for coming. Early in the morning. I'm just jet lagged, so I woke up at 3 a.m. But if I was in New York, I'd wake up at 11 a.m. and I would miss my talk. Okay, so today I will be talking about generative models. A little bit about generative models for images and videos, but generally generative models, and also I will talk about models that are built for generating images in general, and I will also be talking about different approaches you can take to generative modeling, not just adversarial networks, but other kinds. And then finally, I will do a thorough introduction of adversarial networks. So let us start with this picture. So here there's a man who's kicking the football, and there's a goalkeeper who has to stop the football, right? So now if I ask you, where is the ball going? Will it go here? Will it go here? And if I ask you that, you can try to think. You could be like, oh, I see the leg is going like that, so I think it will go to the right side. And like in your head, as a human, you are making all these reasoning on which way the ball may go, and then you can assign a probability to like every part of the picture. What is the probability of the ball going to a particular place? And that's this one. This one. Okay, perfect. So if I ask a question more precisely, what is the probability of going to, let's say this is x equals 20 and y equals 30, then you can try to build a model that says, oh, this is, so maybe this is some player you know, and he always hits to the right, so the probability of getting here is more than 0.5, and then you can do some more calculations. In your head, you're essentially building a generative model of this process of a man kicking a ball, and then you're assigning some, you're creating a distribution of possible samples, possible locations where the ball will go. And this is essentially, you're building a generative model of a man kicking a football into the goal. So formalizing it a bit more to problems we care about. Let's say you want to generate an image, not just of someone kicking a ball, but any image. Then you can think of it as there is some generator, some black box, which takes in some input. It could be some things about the prior of the situation, like, oh, who is this man, or like, what angle is he in right now? And then you can generate some output. In our field, usually this generator here is a neural network. You take in some inputs and then you generate something. And that could be a distribution, it could be a probability distribution, but it doesn't have to be. It could just be an arbitrary distribution of images that doesn't have a proper probability defined. And then you can also do conditional generation. Let's say you give one number between -10 and 10, and if it's -10, you want it to generate a dog, but if it is 10, you want to generate a cat. And everything in between, you will have some kind of smooth function in this latent space. This thing here is called the latent space. This is called conditional generation. So the conditional latent space in our example here is, oh, if the player is right-footed, usually where will the ball go? Oh, if the player is Ronaldo, where will the ball go? The general motivation for building generative models is that just like we humans think and reason about a situation, and we want to predict the future, and then we can make better decisions on what to do. Similarly, if you have a generative model, you can somehow conditionally generate your conditions and then predict some part of the future, and you can make better quality decisions. That is one fundamental motivation of building generative models, among many. Now, you could think of, okay, what you asked is generation of like where is the football going? But why do we care about image generation? Like, why do I want to start from nothing and generate a full image? For that, I will introduce a concept called unsupervised learning. So in general, if there's a machine, some learning machine, it could be a human, it could be a neural network or anything. It takes in some inputs and it will get some outputs. And then the outputs have to match with some targets that are expected to be happening. And you get some feedback from these targets. Now, if these targets are external, that is, their targets are provided by someone else. Let's say that you have a data set of images and whether the target is a cat or a dog. Then the targets were provided by someone else. They're called the ground truth. And so this setting is supervised learning because the rewards you get are external. You also have this other setting where you, in the black box, the neural network itself, generates the outputs, but it also has some targets that it generates for itself. And in here, it's learning on its own. There's no targets. There's someone else outside of the neural network is not telling it what to do. It is just self-playing some game and trying to be better. Now, generally, this green box is a neural network with multiple layers. Let's say our problem here is to initially build a generative model of images where it will take in a lot of images from the real world and it will learn to generate outputs, which are images that like over this training process, it will take in some random inputs and it will generate images of the real world. Now, let's say this neural network has a new problem. It has to classify cats and dogs. It gets some new input and it has to classify cats versus dogs. Because the neural network has multiple layers, it learns a hierarchical representation, you can reuse the layers from when you did the first task to do your second task, which is like classifying cats versus dogs. So these yellow layers will be new layers that are specific to this new task, but the blue layers are shared between the unsupervised learning and the supervised learning. What actually happens because of this is the amount of data you need to have to train on a new task is reduced by a significant amount. So, for example, without the unsupervised layers, if you want to do cats versus dogs classification, let's say you want an accuracy of 90%. Then, without the unsupervised learning, you might need 1 million images. But with the unsupervised learning, you might need only 1,000 images. So the amount of data that you need is heavily reduced. So that's the motivation for building generative models of images, where we want to build a generative model for images, and we want to reuse these models in other settings. So there are many different approaches of generating images in research and literature. I will go over a few of them. Let's start with wavelet-based methods. There are many classical methods. I will just go over one of them, where you have traditional signal processing, and you have wavelet theory and stuff. So in this particular paper, actually it's a group of papers, what they do is they're trying to generate textures. So you are giving to the model this center patch, and then the model has to generate more texture, like on the sides here. Similarly, you give this center patch and it has to generate everything on the side. And the approach they take is they send the center patch along with some kind of some output padding into a standard wavelet transform, which has a high pass and a low pass filter. And in the high pass, you just pass through, but the low pass, you basically recursively take more high pass and low pass. Like, so you take a few bands here, and then you again do a low pass over here. So in this approach, what they do is in this particular black part, they again put one more system just like this. So it's sort of this recursive wavelet thing. And then what they do is they try to match the statistics of the boundaries, that is, of these regions, to be the same statistics as this region of the filter passes. And then they optimize. It works well for textures. So if you want to just have these bricks, and then you want to have more bricks, like these repeated patterns, it works reasonably okay. But if you're trying to do something close to natural images, then it does not work. It's very limited in its scope. Another classical method I will show you is called image quilting. It was also published early 2003, I think, at SIGGRAPH. And the approach is as follows. You take an input texture, and then from this small input texture, you want to make a very large texture. So what you do is you take random patches from this texture and then place them next to each other. And then you will see some artifacts if you place them next to each other, you will see that they're not exactly matching properly. So then what you do, you add some overlap textures. Instead of like just putting blocks right next to each other, you have some overlap. And then you put some constraint that the blocks have to match in correlation at these overlapping edges. And finally, to reduce the edge artifacts even further, you have some kind of graph cut algorithm that will make the texture even smoother at the edges. It works pretty well on textures. Actually, it works very well on textures. In fact, it works even well on, let's say, to generate text. Like here, you give this input patch and you say make more, generate more text, and then it will just generate a large amount of text for you. And it can even do things like style transfer. You can take some source texture and some target image and say, I want my target image, but in the source texture. And what you do is you take patches of the source texture that have some matching statistics with blocks of the target image. And just doing this like random, applying these patches randomly, actually works decently well. However, it does not work if you want to do like full image generation of, say, natural images and stuff. If you want to get a full object properly unsupervised, like if you want a bike or something, then it doesn't work super well, because it's the reason is because it's a local placement-based approach. And then finally, coming to the neural network world, there are these sets of algorithms called auto-encoders, where what you do is you sort of make a bottleneck layer, like you reduce the size of your inputs to the next layers of your neural network until there's a bottleneck that is formed, and then you expand it again. So during a training phase, you get some input, which is a natural image, and then you will squeeze it into some code, Z, and then it will again try to reproduce the same input. And you will take something like a mean square error between x and x dash. And if you want to generate new images, what you do is you ignore this first block, you just generate some random Z, and then you try to see what x dash is produced. Extending this, there are actually many different variations of autoencoders. There's probably like 20 of them just on the top of my head. The typical characteristic of autoencoders is that you have a blurry generation. And one second. This is because between x and x bar, you usually take some kind of loss based on KL divergence. That is, you'd say you take a mean square error, then mean square error, for example, will give you better loss if the image is smoother, if it's very blurry. And so you typically see these artifacts in autoencoders. Then there are models that are more popular and recent called variational autoencoders. And this is a figure I took from a tutorial on VAEs. So in this, what happens is you have some image X that goes into some encoder, which is a neural network. And then you predict some mean and standard deviation of some distribution. And then those will be given to some random number generator that will randomly, from this mean and standard deviation, they will sample some latent space, some random number, and then that will go to a decoder that will try to generate the image. It's again another neural network. And you have two losses. One is whether the input X matches the decoded image Y, and then the other is whether the mean and standard deviation that are predicted are close to the dataset's summary statistics. This works much better than standard autoencoders, but again, this also has this distinct characteristic of it has a lot of blurry images that are generated. And then there are the next kind of models, which I call auto-regressive models, which basically they try to predict sort of recursively. They take a smaller patch and then they predict a larger patch, and then they take this larger patch and they predict a even larger patch. So one of the models, as an example I want to explain, is this model from DeepMind called Pixel CNN. In this model, the image that is generated, the way it is done is you go from left to right, and you predict one pixel as a conditional on the previous pixel. So let's say you're predicting this this guy, this black pixel here. Then you're looking at some neighborhood of this neighborhood here to predict this one particular pixel. But that neighborhood is, it sort of has blind spots, because let's say you want to predict the first pixel, then there's no neighborhood for it, right? So it has a little bit of blind spot, and I think they just like randomly generate some initial neighborhood, or they have a prior over the data set. But basically it's just like, you will go line by line, or you will go like neighborhood by neighborhood and predict pixel by pixel. These things, they work pretty decently. So this is a figure where you are given this guy, I think, and then it's predicting multiple images starting from this particular seed. And that's pretty good compared to Auto-Encoders. And next, you come to Generative Adversarial Networks, which are the main topic of this workshop. But I just wanted to make sure that you knew a lot of other models existed for generative modeling that are not adversarial networks. So adversarial networks were introduced by Ian Goodfellow and team at University of Montreal in 2014. And the way they work is the following. You have some input noise that is given to some neural network, which is the generator, and it will produce some image. Now, if you remember in Auto-Encoders, this sample is compared to the original sample with some loss, some mean square error. But instead, what you do, this is basically what is the regular models. The sample goes into some loss and then is compared to the training data, and the loss is something like, does this look something similar to the original training data? And the problem is coming up with a loss that says, does this sample look like a sample from the training data? It's very hard to come up with such a loss. Think about it. If you are given a picture of a cat, and you have to come up with a mathematical loss function that says, that gives you some score on whether it's a cat or not. It's pretty challenging. It's definitely not going to be simple. So this is one of the primary reasons why you can think of the Auto-Encoders not doing super well, because coming up with a loss function for a very complicated distribution is hard. So what adversarial networks do is they actually, the input noise goes into a generator, it produces an image, and then that image goes into a discriminator, which is also another neural network. And this discriminator, it will predict whether this image is supposed to be real or fake. Fake means it is from the generator, real means it is from the input data set. And this output prediction is trained with standard log loss. So you can think of this system as you're learning a loss function. You don't know how to come up with a loss function for a very complicated distribution to match something in the distribution, and so you're saying, I will just learn how to predict whether something is from this distribution or not. Now, it is trained via gradient descent, like all other neural network procedures. The way it works is it's an alternating optimization. So you have, when you're training the generator, you are trying to maximize the chance that this will fool the discriminator. That is, the discriminator will predict that whatever sample here is, it will be classified as real. And when you're training the discriminator, you're trying to do the other. You're trying to make sure that you're not being fooled by the generator. That is, the generator sample that comes in, it has to have a maximum probability of being fake. And in the original paper, the generated samples look like this. This is trained on modeling the CIFAR-10 dataset, and these samples don't look very good, but like for back in the day, like we thought this was a very promising set of samples. Now, in the original generative adversarial network paper, it introduced a very powerful concept, and it showed some very good results. But there were some drawbacks that several papers followed through with. One is, in adversarial networks, they did not propose how to have the noise not like be some kind of conditional space. So let's say you want to tell the network, generate a cat or a dog or a bus according to what is given over here. That conditional generation wasn't proposed. And the second thing is, because this is it's a minimax game where your generator is doing gradient descent in one direction and then the discriminator is doing gradient descent in another direction, it's actually a very unstable training procedure. Compared to if you have a standard classification loss, then you just go in one direction, which is I am trying to minimize my loss function. So because this is a minimax training problem, the training is much more unstable. And what do I mean by unstable? I mean, if you try to train a GAN using a different neural network architecture than that is known to be stable, then it won't work. Also, if you try a different data set, it won't work. And if you try, instead of image generation, if you try video generation or text generation, it won't work. Now, and the last problem is there's no way to evaluate generating images from GANs other than looking at the image and saying, this image looks good. So these are all problems that some of them have been addressed by follow-up research, and some of them are still open problems. To start off with conditional generation, we introduced conditional generation in our paper in 2015. The paper covered conditional generation, and it also covered a new architecture that is much more stable and can produce high quality, larger pixel images. So what we did was we just said, apart from the noise that the generator takes, you also take a categorical variable that specifies which class you want to generate. It's a very simple proposal, and it works pretty well. So when we ask for an airplane, it would give airplanes. When we ask for automobile, it gives automobiles, and so on. It actually does very badly with frog. But if you think about it, frogs are, they have evolved to avoid detection. So it's very hard to actually think about generating frogs. Then there's a whole set of new papers that came that try to improve the stability of the architecture. It's like, if I use this particular architecture, it will just work across many problems and many domains. The first big one was DCGAN, which I co-authored, but it was mostly Alec Radford who did the majority of the work. We proposed a simple, what we did was we just searched and searched and searched manually and found that there was one class of architectures that was very, very stable to use with GANs. And it had this structure where you incrementally double the size of the resolution and you keep the same convolution filter size and so on. It's just an architecture paper. It's like, if you use this particular architecture, it will work. And we showed some nice results. These are results of bedrooms being generated. And we also had some face results. And then we had one thing we saw that was cool was you could actually generate some faces, and then you could take the latent variable, that random variable that generated the faces, and you can start doing arithmetic in this latent space, and you will actually get semantically meaningful generations. And this was somewhat surprising because, remember, the network does not know anything about sunglasses or anything. All it knows is how to generate faces. So that was interesting. And another thing that we did in DCGAN was, remember when I said the original motivation for doing the generative models is so that you can reuse the representations? We did exactly that. What we did is we trained to generate house numbers. So in the front of your house, there's a door, there's a number, and so Google published a data set with a lot of these house numbers. And one of the challenges was like to classify the house numbers, and they had 700,000 labels. But what we wanted to do was to train unsupervised on the 700,000 images. That is, you don't show the label to the network. And then, can we just use 1,000 labels and then get to a good accuracy? So it is this problem where in this part, in this unsupervised part, we use all the images that we have, but no labels. Like if you are given an image, I won't tell you whether it's a 0 or a 9 or a 3. And then in this part, you are given labels, but you only have 1,000 images. So the motivation is you just like, let's see how well it will do if you reuse the representations and you have much lesser label data. So just with 1,000 labels, at that point in time, we reached state of the art compared to all the other unsupervised learning models. And one interesting thing is just 2 years prior to us publishing this paper, I published one other paper on using all of the 700,000 labels to build a supervised classifier, and it was at 95% or something. Like, it was pretty close. And then there was a follow-up. There were several follow-up papers that showed that using GANs, you can actually get the classification error just with 1,000 labels down to less than 5%. So that's very interesting for me because one of the challenges we have in machine learning is we have to collect a lot of labeled data. We have to collect 1 million samples with some human somewhere labeling, oh, this sample is this sample is this, and so on. If we can instead have very little labeled data and have a lot of unlabeled data that's easy to collect, then that'll just accelerate progress in machine learning. So that was DCGAN. And then StackGAN was this paper that's published from Rutgers and CUHK. StackGAN was just, again, just like DCGAN, it was an architectural improvement. So what they do is they say that if you use this particular structure of your network, where you recursively stack a whole generator and then upsample it, somewhat similar to the LabGAN architecture, then your GAN is much more stable and it can produce better images and larger images as well. As an example, here are pictures produced by the StackGAN architecture. And finally, very recently, some researchers from NVIDIA have published really good results. Again, using, they propose a new architecture that stabilizes GANs even more. And they call this progressive GANs. And they have shown for the first time really good results, which even humans are being fooled by. So the architecture is as follows. What you do is you start small. You start with one layer of a generator and one layer of a discriminator. And you start playing, you start training. And once this is trained for a little bit, then you add a new layer. You add a next layer and you train for a bit more. Once this is trained, you add more layers and so on. So as training progresses, you keep adding more layers. And so you start from generating a very small 4x4 image, and then you start generating 8x8 with 2 layers, and then so on. And finally, with the multiple layers, you're generating a 1000 by 1000 pixel image. And there's some subtlety to this. The way you add new layers is important. What they do is, when you add a new layer, they have some scaling factor alpha. It's too small to see here, but where you slowly fade in the low resolution. Initially, you start just with the low resolution because you have a shortcut pass, and then you slowly fade in the image generated by this newly added layer. And once this is well trained, you just like remove this shortcut pass. Because of this smooth transition, it's supposedly much more stable. And these are images generated by the progressive GAN. These are not real people. So it was very impressive to see these results. And then I discussed all the architectural improvements. I did cover all papers in the field, but I covered some of the most popular ones. Then there is the optimization improvements. So you can add a regularizer to your gradient descent algorithm to make the training more stable. I'm not going to go into detail, but one of the most popular regularizer terms that are proposed in multiple separate papers is that you penalize the norm of the gradient. That is, you make sure that the norm of the gradient is within some bound. And that is a sufficient penalty for the training to be much more stable. Effectively, what you're saying is, if the generator is trying to go too fast in some direction, don't let it, like make it go slowly. And similarly, if the discriminator is trying too fast to learn, slow it down. And so it's essentially this like slow learning process in all directions. Intuitively, that seems to help. But there's a lot of theory that was developed to justify this, along with mathematical proofs that this is a good solution. And another recent paper, it's still anonymous, we don't know who the authors are, but at least I don't. It's called spectral normalization for GANs, and it just says, instead of taking like the L2 norm or like L1 norm, if you take the spectral norm, then the training gets much more stable. And there's a lot more in the paper, and it has really cool results as well. And coming to evaluation, one of the problems with GANs, as I mentioned, is the only reasonable way to evaluate in the original paper was to look at the samples and say, oh, this looks nice, this is working. But what we want is to be able to evaluate automatically. We want to be able to say, oh, let me take my generations, and then if I run it through some evaluation score, I can tell whether it's good quality or not. But then it again comes back to how to define a loss function that showcases, that like a powerful loss function that can tell whether your generations are from the real distribution or not. There are two scores that are proposed: inception score and the Frechet inception distance. The inception score says if you run your generator through a standard connet that is trained on image classification, usually on ImageNet, then and then you take some statistics in particular places of the network, then you can roughly say something about the quality of the generation and like how close they are to real generations. It doesn't always work, but it is one of the metrics that is proposed, and Frechet inception distance is like extending inception score to be a bit more robust. And then we propose a score. This is not exactly a score. It's like when you're training, one of the problems with GANs is there is no concept of the loss going down. So you're sitting there, you started a training run, you don't know like whether the GAN is working or not. So for that, we propose to use the Wasserstein distance. And if you have your GAN be of a particular formulation called a Wasserstein GAN, then you can use the Wasserstein distance to monitor whether your training is working or not. And then let's come to applying GANs in other domains, not just image generation. But also not just like unconditional generation, but also other problems like text-to-image generation and so on. So the first thing I want to discuss is generating videos, video prediction GANs, either conditional or unconditional. That is, conditional is you take the last X frames of a video and then you want to predict the next frame of the video or the next 2 frames of the video. Unconditional is you just want to generate a video, period. So starting with conditional generation, one of the papers I wanted to discuss was this particular paper that tried to do video prediction, where you take a video and then I will show you an example. But what they do is, apart from just having a standard GAN, they do one additional thing, which is they add a mean square error loss to the sample. So now the sample has 2 losses. One is a standard GAN loss, and the second is an autoencoder like mean square error loss. And what the problem is you are given these input frames. These are 4 frames that you are given, and then you have to predict the 5th and the 6th frames. So this is the ground truth. This is exactly what happened next. And if you just use a standard L2 based decoder, then it's very blurry, as I mentioned earlier. Also, if you do an L1 loss, it's slightly less blurry, but it's still like pretty blurry. With purely an adversarial network, the image is very sharp, but it does not have any movement. It's like it's just repeating the frames from the previous inputs. With this combined loss, the L2 and adversarial, and they have one more term that penalizes the gradients, I think. It actually provides the best result. These both actually provide good results, and this, like, if you actually measure like measure the results, like this particular hybrid loss structure provides the best result. The next application I want to show is in painting. In painting is this problem where you have some image and then you remove parts of the image. Let's say you have a photograph that is 30 years old and it has lots of scratches and or like, you know, some part of it tore off. So you want to simulate that. You just like remove the part of the image and you want to have models predict what is supposed to be in that part of the image. And for in-painting GANs, adversarial networks actually do pretty well. So on the left side is the image with some white slot, and this is the GAN filling up the image by itself. And you can see like almost all of the results are very clean. So like if you look at this thing with mountains, and in the middle you remove the block, it actually filled up like the mountain going, then another mountain starting, so it's pretty good. And now if you compare this with other models, so just as a brief example, this is an input with this center block removed. This is what a human artist says there should be. This is L2 loss based encoder-decoder architecture. And this is the L2 plus adversarial. It's again, in the in-painting paper, this paper was from Berkeley as well, from one of the original authors of the image quilting. They do a combination of adversarial loss and the L2 loss. And this hybrid model, again, seems to be working better. Then let's look at text conditional GANs. What this means is you are given an input which is a text, which is, let's say, a man is sitting on the beach, something like that. And then your output has to be an image describing that text. It's a pretty challenging problem. A lot of people tried it, and then the first time there were good results was from this paper in 2016. It's the way they pulled it off is, again, it was an architectural paper. They were like, you have to be very careful about how you build such a model and how you encode the text and how you send it to the generator and the discriminator. They released the source code, which was helpful in reproducing it, but like there were so many details in the paper which showcased how unstable adversarial networks are. They, like, for example, some of the choices were like how to encode the text. Like you have to have a separate, like, special binary mask encoding that they came up with arbitrarily, and only then it worked. If you just encoded it with like a standard one-hot encoding for the text, then it wouldn't work. But the results were actually pretty good. Here are some examples. Here's a caption which says, a pitcher is about to throw the ball to the batter. Baseball is popular in Taiwan, right? So, yeah, this is a baseball setting where the pitcher is throwing the ball to the batter, and then the network generated 16 images of different kinds, which tried to be what this caption said. And similarly, it says a group of people on skis stand in the snow. And you see all the background is sort of mountainy and snowy, and there's a bunch of people in the foreground. So it did pretty well. Generally, back then, when we saw these results, they were pretty impressive. Similarly, another example is like, this flower has white petals and yellow stem, and it exactly draws this flower, which has white petals and yellow stem. Again, if you ask for dark purple petals and yellow inside, it draws that, and so on. And the third data set they showcased results on was this birds data set, where you can describe the bird, and then it will draw a bird of that particular nature. It was generally pretty impressive. And then the last class of work I wanted to showcase was something similar, like another domain adaptation problem. This is called image-to-image translation. So you have two sets of images, one taken in some conditions and the other in some other conditions. And can you translate both of the images? As an example, you open Google Maps and you have an input, which is the satellite image, and then you have the output, which is the regular vector form. And can a neural network take the satellite image and automatically generate the vector form and vice versa? And another example is you just draw the sketch of a handbag, and can the neural network generate a handbag with texture and so on? And another interesting example is you have an input which is a picture in daylight. Can you generate the same picture but in nighttime conditions? The interesting thing about this work is all they had was whole sets of images in one condition or another, and then the network could automatically translate between one domain to another. They had multiple tricks. They had architectural tricks, and they had some loss function penalties and so on. The other paper, also from the same lab, again, this is all from the lab that the guy who did image filtering, is another paper with similar motivation. You are doing image-to-image translation, but in this first paper, you were given the exact pairs of images. That is, you were given, okay, this is my input, this is my particular output in the other domain. Like if this is my black and white image, this is my colored image. You had some ground truth pairs of images. But in this paper, all you had was one data set which is horses, and another data set which is zebras. And then it automatically figured out how to generate the zebras from the horses and so on. So as an example, you give an input as a horse, and then it would generate the same picture where the horse is transformed into a zebra. So this is much more impressive because it removes the supervision even further. It says, I do not need any particular one-to-one mapping between domains. Now, finally, I want to talk about some still open problems in adversarial networks. If you look at all my slides, if you look at my original, where was this? Oh, there's a lot of slides. Oh, there. If you go to this particular slide, I showed how we have improved the architectures. I showed how we tried different domains. And I did not cover text and speech. I think that will be covered by a subsequent speaker in the afternoon. I said there's no way to evaluate other than looking at samples, and I showed that there are some metrics that people propose, like the inception distance, that are somewhat there. But there's a lot more to do in terms of the stability of training. We still don't have GANs working for text properly. And we don't have it working for speech to a large extent. And so the open problems are stability of GANs, basically trying to attack new domains like text and speech, and you help improve the generation process there, or even generative models in general. And then the evaluation of generative models. This is a completely open problem, not just across GANs, but across all generative modeling. If you have built a generative model, how do you evaluate the quality of the generative model? There's a lot of solutions that are proposed, but none of them has stuck in the community. And the third and very important and very challenging problem, I think, is long-term video prediction. So if you go back to the original particular example that I gave, there's a man who's about to kick the ball, and think about the goalkeeper. The goalkeeper is trying to judge at every particular second where the ball is going to go. And the goalkeeper doesn't have enough time to see the ball start moving and then go in that direction. The goalkeeper has to make up their mind much before. So having a long-term video prediction generally will allow you to do what is called model-based learning, where you, as the like artificial intelligence agent, have a model of the world in your head. And then in this model, you can simulate what is going to happen and predict some high quality scenarios, and then choose between them. Long-term video prediction is one big part in that particular scenario. So with that, I stopped my first part of the talk, and feel free to ask questions.
Okay, we have some time for questions. Yes.
Oh, hi, Soumith. Thanks for your talk. And I'm more hardware guy. And for your problem, I have one question. In which scenario you prefer to use GAN or autoencoder like this? Because I'm wondering the cross-domain problem. Like now, I ever know a sensor called jog site. Like my input is force sensor. the output is a depth image. How about I wondering, reverse the order, like I see an image, then I output a false, predicted false. Is that a related word related to this scenario?
I don't know.
Because
really
I see mostly like video or image.
Right.
Yeah.
So I think my view is you always want to use some kind of hybrid loss. You want to use a loss which has one adversarial term and also has one L2 term. A combination of these keeps the training stable and it will give you high quality sharp predictions. But if your domain is not really generation, like if you're saying, I want to predict whether some particular decision is taken or not. So if I'm given an image and I have to predict whether the balls are falling or something like that, then for that I don't need an adversarial network, I just need a standard classifier. It depends on the problem, but if you're doing a generative problem, I think a combination of adversarial and L2 helps.
Okay, thank you.
Any other questions?
I have some question about, you have mentioned about the evaluation of generative models is a problem in the game. I know at the same time when the W game is published, the same time have another paper is mentioned about LOS game. And in some discussion in China also discussion about the general loss sensitivity. But I still try to study about this region. So I want to know if you have any idea about this. Could you share it to us?
About which part of
loss sensitivity.
loss sensitivity? By loss sensitivity, do you mean like the loss being correlated with the quality?
In this discussion, they mentioned about the game will strongly affected by the define of the function. So let's talk about why the original setting will make the mode collapse, and let's try to study more about how to make the loss define more make sense.
Right. I don't have any good answers to this. I think it's still actually the WGAN paper around the time we published it. There's other papers as well who studied this. I think practically none of them worked in all of the domains. So like, I don't have a concrete answer on like what the direction of the field is taking here.
Hi, I have a question about mode collapse. In your view, why and how will have a mode collapse problem, and we have a solution to solve this mode collapse problem is because of K-load diverge or other kinds view and things.
Well, mode collapse, it's kind of interesting, and I think GANs have mode collapse a lot more than KL-based losses, because KL-based losses are basically enforcing cover as many modes as possible, right? Just like have some blanket over the entire high density areas. GANs are not doing that. GANs are basically the original GAN formulation is optimizing the Jensen-Shannon divergence, which is much more relaxing. It's like, well, I will give you good loss if you cover 2 of the modes then have like some blanket over all, over the whole mode. And the other thing is, I think GAN training itself is not super stable on what divergence it is actually optimizing. Like theoretically, you can say, okay, the original GAN formulation optimizes Jensen-Shannon, or you have these F-GANs, which are like you can precisely specify a GAN procedure that minimizes some F divergence of your choice. And then you have the Wasserstein GAN, which tries to say, I won't do divergences, I will optimize the Wasserstein network. But practically, none of these are stable. So none of these are actually optimizing the loss that they're supposed to optimize. And I think mode collapse is sort of an effect of that, and some of the divergences are much more relaxing to not predict certain modes. I think if we answer the stability question a lot more, like, okay, if we can make the GAN optimize whatever cost function it is supposed to optimize, then we can study the mode collapse problem much better.
Hi, Soumith, is Facebook using GAN to classify inappropriate images?
So I actually can't talk about any Facebook systems. One, like I actually don't work on any of them, and 2, it's just I was not given clearance for that.
Okay, thanks.
Thank you for your talk, and because I have tried some training tricks from your GitHub repository called GLHex, and I want to ask a question about that. Why we need to reverse the labels while we are training the generators? Thank you.
Honestly, in the code, that's what I found the easiest to do. So that's what I was doing. So when I wrote the code for LAPGAN and DCGAN, I'm like, oh, what should I do here? And then I just like flipped the labels, and it sort of worked. And then I worked the formula backwards. I'm like, oh, this is a formula that we're actually applying to reverse the labels.
Okay.
Thank you for the speech. We know DCGAN is a good structure, and it must spend a lot of time on try and error. So would you like to share some tricks how do you save the time to tune in the structure?
Yeah, so DCGAN was interesting. It was actually the first author, Alec Radford. He was working at a startup, and in the weekends he wanted to build better structure. So he just manually, he would keep exploring different structures, and he would try changing the type of pooling and add batch norm and so on. And then he would discuss this with me. He's like, oh, I found this thing. What do you think I should do next? And then I gave him some suggestions, like, oh, apply this to semi-supervised learning, and this is how we construct the experiments. And so most of the exploration was a little bit of intuition. It's like, oh, I tried 10 models. Okay, this is what seems to be working. Okay, let me go in this direction. That's what happened with DCGAN. But these days, you have many papers that are exploring oh, you can search for an architecture. The problem with that is there's no good way to evaluate generative models. So if you try to do some kind of automatic search, then, and let's say you're only optimizing for inception score or something, then it might just overfit to the score, but might not provide good images. So yeah, back then it was just like trial and error, like some intuition, and not sure like how it could apply to general meta-learning search.
Okay, I think it's about time, and we still have time for questions in the second part. Okay, let's thank Soumith's wonderful talk for the first part, and then we can go.